Yeah, thank you very much for the introduction. If I'm speaking too loud, just tell me. I have a really loud voice, and people always complain about it. So just to make sure before. So I want to take you on the journey to figure out what EyeSee360 is. And I would like to start to introduce my topic with a situation that's maybe not familiar to every one of you, but it's a good example to show where my technique is, or our technique is required for. So imagine you see like on the left side, this image is like a ship which is currently docking. It's like a big container vessel. It's like over 300, 400 meters. And you're like the pilot standing on the ship bridge, and you want to bring this ship into a docking position. What you do normally is you're standing on the starboard side of the ship, which is like the right side, for just to mention it. And what you have to do is like really observe all the time how the ship is approaching. So because like the slightest movement tells you already about something that's maybe wrong, some force has to be changed or whatever. And at the same time, you're communicating to, in this scenario, there are just 2 tugboats, but for these bigger vessels, there are even up to 5 or 6 vessels or tugboats you have to coordinate during this docking process. So that means you're giving them some like a position where they have to go to and which force to pull or to push onto the ship, but you don't have any way to figure out if they really do what you want them to do, because there's like, you can imagine like walkie-talkie communication is going on, and there's a lot of interference, maybe a misunderstanding. So there were many accident reports stating that these tugs can easily canter, and they have like really to trust the pilot that he's giving the right decision to pull the force at the right spot. So there were many people dying actually in accidents where there was a misunderstanding in the scenario. But to bring it more on a more abstract level, what's going on here? There's a primary task going on. The primary task is requiring the user's focus, but at the same time he has kind of a secondary task where it's about like monitoring and observing this out of view objects. To give examples that are maybe better to understand, there's for example this gaming scenario. You imagine like this, like a game where you have a spacecraft and you kind of like freely fly in 3 dimensions, and you have like also like fighting scenes where you have to fight other ships. And there you also have like the primary task. You need to know what's directly in front of you, maybe like attacking a ship, but you also have to be aware of all the other ships around you. And it's the same for driving also. If you're sitting in a car, you have to know like where other cars around you are, even behind you and stuff like that. So coming from that, we can set up some requirements for the secondary task here. What we want to do here is visualize the position of these out-of-view objects. And we want to do this in 360 degrees around the user, which is like sufficient maybe for a car scenario, but we also need like for the 3-dimension things, like also ship bridge has like the tugboats are they are on the water level, so you have to look downwards to get to them. So we have also like this 90 degrees of up and down. You have also multiple objects, so not one, but more than one. And what's also important, because of the primary task, your focus needs to stay uncluttered. So we cannot put information into your focus because you need that. So that brings me to the question, why would we like try to visualize these objects? One could also argue, okay, you can use like tactile or auditive modality, even combine them or whatever, to somehow visualize or to somehow show where these objects are. But since we have in most of our scenarios multiple objects which have like changing positions, so imagine like the driving scenario, car is fastly approaching, so it's changing the position really fast. And if you want to do it with multiple changing objects, it's quite hard to encode that in tactile or auditive feedback. You would like end up in fatigue, or if you will end up like everything is vibrating. And this is not what we want to do here. So therefore, I was thinking of staying with the visualization of these out-of-view objects. There's a lot of related work going on that, because there was, during a time a few years ago, or in the beginning of the century, there were lots of people looking into off-screen visualization, which is quite close to this topic. Off-screen visualization means that you have a smartphone which has a limited display, which is quite small. And if you imagine, for example, you have some map task where you are really zoomed into the map because you want to navigate currently and see what's the next street to go to, but at the same time you want to know maybe information about point of interest, where's the next gas station to fill up the car, and they're maybe off screen. So therefore, people were coming up with lots of different techniques here to show these objects. And I just put here a selection. In my paper, there's a full bunch of those. It's really also a nice place to look up what was going on with off-screen visualization so far. And we have this first 4 techniques, where basically really this off-screen scenarios where we don't have head-mounted devices. So it's basically, you can imagine even if they are augmented reality, it means you have kind of a smartphone in your hand holding it around. And then there was recently a jump to go to also use these head-mounted devices, which is really interesting with regard to all the new augmented and virtual reality devices that are out there. But they had the problem here, as you can see, attention funnel and power frustum both only look into single objects, not multiple objects at the same time. Okay, so there is another conflict we have to solve somehow. Coming from the requirements, it says, okay, focus needs to stay uncluttered, but okay, where to visualize then? So and there was our idea was to put the information in the periphery. So as we all have kind of a natural understanding of what's going around or happening around us, just in a limited 180 degrees field, we know if something is happening in the periphery, we can move our attention towards this thing that's happening or going on there. And basically my idea was, or our idea here was to extend it to 360 degrees around the user. We were inspired by edge radar, so edge radar, which was a technique coming from the screen again, which was using borders around the screen to indicate off-screen objects. For example, the red ones here are off-screen objects, and the blues are the representation of these objects. So we took this one and brought it to a head-mounted device. The first thing we recognized was, okay, one of the bigger struggles people had with off-screen visualization was the rectangle shape. So they had the corner density problem, for example. You can imagine this part here is showing this complete area, while this tiny little corner here is showing this bigger square down there. We don't have that problem here because due to color perception and perception, how human perception works, a ellipse shape is way more natural than using a rectangle shape to show the information here. Additionally, we were thinking about, okay, 3D position is having a new dimension is coming in here. That's maybe too much. How can we do that? And our approach firstly was to split it up. We basically split it up between what's the direction of the object, which is also this natural kind of, okay, when something is here, I can assume it's somewhere there. So splitting up what's the head direction, or my current direction towards this object, and then encode the distance on top of that. How close is that object? Which is also natural for, imagine the car scenario. It's maybe cool to split it up because then you can sort by distance and can fast see, okay, these objects are closer or these objects are far away. So this is basically the foundation where we started. Like EyeSee has like this 360 degrees around the user, as I was mentioned already, and it's like represented by this ellipse, where we can say like this is like 180 degrees right behind the user, while this is like 180 degrees left behind the user, which brings us to one minor limitation here. Objects start to jump between these versions, which is like, yeah, maybe in a newer version we will fix that, but I don't know how. And we have like 90 degrees up, like it's like really above the user or underneath the user here. And we have in the middle a new shape which is representing our natural field of view. So this is the part we can see. On the left side you see it's the natural field of view. It's like what a human can see, like it's 180 degrees splitting up, so it's also kind of an ellipse. So that part we can observe by ourselves because it's something that's what we can perceive. And on the right side you see this rectangle shape, which is like a representation of a limited field of view, which is like the case for every VR, AR headset. Because this is like, for example, imagine the HoloLens has like it's not big, not that big, but for example, it's more like an Oculus here, which is like limiting our natural field of view. So, but we can take care of that with like different shapes within that. Okay, what we did then was creating 3 different versions of our EyeSee variant. So, as you can see here, each dot is representing like an object that's out of view. And I wanted to show with this one because it has also like these lines, like these are the null lines. That means like horizontal and vertical null lines, which is like directly in front of me or on the same height than where I'm currently. And then we added like, or introduced 45 degrees help lines, which is saying basically when you know like one help line 2 means like 90 degrees, slightly above, so you know exactly, okay, this object is there, without even looking and figuring out if it's there. Yeah, we tested these 3 versions, which have like kind of different kinds of help or assistance, and we have like different encodings for the distance here. We use here a gradient from yellow to red, and on the left side also there's like size, like smaller is far away, bigger is closer by. And the last one is a combination of them. Okay, to test that out we needed some kind of prototyping tool to fastly see how people think of that. It's really big, isn't he? Oh, awesome. Okay, so what we did here was like a really easy, rapid prototyping AR tool. We just use a laser cutter to put some plexiglass together and have the possibility to put in like kind of film slides, like foils, in front of the user. What one has to think about here is we need like a bigger distance than normal head-mounted devices because we don't use lenses here. That means we need to go to that point where the human is able to combine left and right eye view. And also, it's not the best prototyping tool for elderly people because they're losing the perception of like something that's really close. So it's really like, I think it's up to 60 years, something like that. We had participants with 62 years or something in the study, and they didn't have any issues, but we would assume that for elderly people, this was getting worse. Yeah, what we did then was kind of a concept validation study. So we created slides based on the 3 versions we had. And then we were asking, like we're showing 4 slides for each of the variants we had. And we're asking for like how many proxies. So proxies are the dots that are representing these out of view objects. How many proxies did you see? What's the vertical direction? What's the horizontal direction? And what's the distance? And in the end, we were coming up with this questionnaire and some Likert scale questions. That is actually, sorry. That is actually how the form looked like. So we were having like this kind of buckets where people could say like, okay, I feel in the horizontal direction it's somehow here, and in the vertical direction it's somehow here. Then we were running the study. We had 90 participants, 8 female, and as you see here, like 61 was the oldest person. We had all corrected or corrected to normal vision, and 11 out of 19 participants had no experience with off-screen objects. So to understand our results here, it's really easy to, let's go back here. So if somebody was, for example, saying, okay, this object is to be in this area, then it was actually in this, then it was like arrow class 1 in this scenario. So it's like, it says like for the horizontal arrow, around like 25% were like assuming the class directly, the direct neighbor class. It looks maybe a little bit like it is a lot, but we don't put in here the people that were right, that were actually like doing no arrow. So overall, it seems to be like around, to calculate, I think around like 30% where the wrong class was given here. And we ended up with a SO score of 71, which is like slightly above average. So what we were getting out of it was EyeSee360 seems to be promising. We wanted to investigate it further. Ellipsis with helpline subjectively and objectively performed best. So people needed that kind of help. And color and both best for distance encoding. So one fun fact, just within the storyline here, why is it called EyeSee360? Okay, basically it was if you put people this kind of radar in front of their head, they were first like, whoa, and then they're looking, and then you're explaining a little bit, and then they figure it out and they like, ah, I see. Okay, so that was the moment where we were coming up with that name. So based on what we figured out, like in the first study, we were building like a video see-through augmented reality application using Unity. The code is open source available, so everybody who wants to try it out can give it a try. We implemented it also for optical video see-through, and we also optical see-through and for virtual reality. So you can use it in whatever Unity project you want to use it for. Okay, then to evaluate the overall performance of our working prototype, we were coming up with some previous work we did, which was presented on Mobile HCI this year. There we brought these three, or Halo and Wedge were the best performing off-screen visualization algorithms, and we brought them to head-mounted devices also. I have to say the limitation here of these algorithms is clearly that they are working really well for objects that are just slightly out of view. But if you can imagine like a halo, for example, which shows like an object would be here, like in the center of the circle. It shows in this case also like the direction where you have to move to. And it's quite hard to understand this when they're not curved and stuff like that. So yeah, but we needed some kind of baseline to test against, so we took that. And we have like two parts in our study. The first was like the direction estimation, where people just had to judge where they think this object is, in which direction, which was actually split up between like 180 degrees and 360 degrees. We had different number of objects here, and we were using all these techniques. And in part two, we were looking into the distance estimation and did a little search task where people had to really like find these objects. I have to say, because there's no distance encoding in arrow, halo, and wedge, it was not possible to use them here as a baseline. Again, we run a study, 16 participants, 8 were female, all had corrected or corrected to normal vision, and in this case, almost nobody had experience with off-screen objects. So what our results show here is, that's the direction arrow in degrees, which means like how much arrow was there in direction estimation. For example, If it was like 90 degrees and 0 on horizontal, this means like we're like in a circle of 20 degrees around that. And as you can see here, EyeSee was performing way better, significantly better than the other algorithms here. So we had like slightly above 20 degrees error, which is still quite high. Even if you imagine like objects that are farther away, that makes this error even bigger if we have it at an angle. So we really have to look into that to make it better. But what it shows that is like currently for state of the art, it's the best way to show like these out of view objects. Also, what's interesting here is we looked like into how much time do people need to figure out where these objects are. So this is like the search task where it was really about like searching this object. You have to take into account that people had to like select the object. So there were like cubes flying around, lots of cubes, also wrong cubes, and people had to figure out where or which of these cubes was the right one. And as you can see here, we had like 7 seconds to find cubes that are really close by, which was like on the same level for everything that was like in front of the user. And then we had like this little peak here, which shows that people had like a little bit trouble of objects that are really like, this was now the area that's interesting because the human cannot normally see that part. So they had first to figure out, okay, it's really like in the half sphere behind me, and that caused like kind of trouble here, so which led to like little increased time in finding this object. Also, yeah, we have like run like this questionnaire. At the beginning we had 71, but as we were now using video see-through augmented reality, people were more like mentioning, okay, that's maybe a little bit, they got a little bit like the first effects of the simulator sickness, because it was like search task in video see-through, you definitely don't want to do that. So it's because like people were trying to really search fast, and that makes the effect even worse in this scenario. But the other algorithms were also used on the same platform. So also video see-through, so they're comparable. And it's just mentioned here, or just have to mention here that EyeSee is like also in that part of field where Halo and Wedge are. From the workload, it's almost like the same. We have like a really high workload, which is due to like all these assistants, like the helplines and everything that goes around there. That was maybe, or is still a little bit too much. Maybe we also look into versions where we like reduce the number of helplines or somehow try to get rid of them. So coming from the general discussion, we argue that even if we implement it in video see-through AR, it's also like useful or usable in optical see-through AR or VR. So that's at least what our implementation shows. And also therefore we did like do the demo here with an optical see-through device, so you can get your hands on it for another platform. And we argue for the usefulness of our lo-fi prototyping tool because it's really simple to test out kind of static designs for augmented reality. It's really like bringing this pen and paper approach to augmented reality. Of course, we have to do more on the ecological validity. So like check out, like going back to the scenarios I was introducing in the beginning and see if it really works there. And yeah, nobody wants to talk about study limitations. And there's like a conclusion and future work is like EyeSee outperforms in this scenario our own developed Arrow, Halo, and Wedge. It can be the groundwork for visualization of out-of-view objects in the future, but of course there's future work needed. Like these are really the first steps into like this kind of area. And we also think about like increasing the focus area even more by compressing like the objects in the periphery and stuff like that. And I would highly like you to check out the demo in the demo session. We have also HoloLens. Woo. So yeah, thank you for your attention.
All right, do we have questions for Uwe? there's one.
Do you think it'd be worthwhile to include any sort of text on the display? You know, this is 90 degrees behind you, because it doesn't necessarily have to be lines and dots. And then there would be 100% accuracy, knowing where it is.
Yeah, that's a good point. I wouldn't use text, because text is like the slowest thing you can ever use for something, because people need like lots of time. But of course, yeah, you could have like a separation between like these two spheres, maybe like the one behind you, the one in front of you. But I think you would end up in worse accuracy, because if you say, okay, how often is it the case that something is really like directly behind you? I mean, that is like really a specific scenario here. If you could like limit the visualization area, like saying, okay, you just need like 5 spots, then of course text would be faster to like distinguish between these 5 spots. But we're coming here like in full flexibility of 360 degree and 180. So from that perspective, I wouldn't use that like with text and stuff. But thank you.
Okay, I have a question. So if the number of object goes up, so for example, we have too much object in the scene, then what's happened? And also, could you please just talk about more about the objects? So you're tracking them inside the environment. They are a specific object, or it could be everything?
So these objects could be everything, which is like we're on a really abstract level here. So that means like, can be, as I mentioned, like a car or whatever. So tracking is not what we are looking into, or were looking into. And what's the first thing?
So the number of the objects.
I see. Yeah.
What happened?
The number of the object really depends if there is like kind of occlusion. So if you imagine you have a scenario where like most of the objects are behind you, and you would like have 10 of them at the same spot, somehow they were overlaying. But if they are good distributed through a space, in that scenario they're not overlapping so frequent, and we had also like variants with 30 out of view objects in there.
Hi, thank you for your presentation. I'm not sure if you cover in your paper, I'm sure if you cover like use cases or applications, but I think one thing I'm interested about is how do you think this can be applied in sports, like training athletes? Of course, it may sound a little bit weird to ask athletes or sports players to wear HoloLens for training, but in a lot of sports like football, basketball, a lot of players, they have to learn from experience or from systematic training, that they have to learn like who are their opponent's players or players on the teammates that's behind them or around them. So I don't know if you have certain applications or use cases such as sports training. Thank you.
I was never running into the sports issue with having soccer, even if I'm from Germany and like soccer a lot. But actually, I think it's more applicable to like esports. I don't want to mention the military scenario here, but for example, if you have like an ego shooter game where you have like a different team playing and you want to know the position of these other players, you can simply sort by color and say like these are the closest persons and which directions are they and what do I have to go or to do, or in which direction do I have to look for facing them and solving that problem. But yeah, there it's applicable, of course, yeah.
All right, then let's thank Uwe again.